Alright, so far we have been dealing with differentiation of bivariate functions. That is, functions of two variables, two real numbers. Now we consider more general functions or mappings like Rn to R or even M for any natural number n and m. Okay, we first consider functions from n-dimensional Euclidean space to real numbers. Most of the results are basically the same or analogous to the case of bivariate functions. Okay, so suppose we have a function f of x that maps a point in n-dimensional Euclidean space to a real number. So that is, this x actually is a vector, n-dimensional vector. Okay, x1 to xn. And we define total differentiability, just like for the case of the bivariate functions. So here's the definition. Totally differentiable. Okay, so suppose U is an open region. In the n-dimensional space, and f is a function defined on this open region U. And let A be a point in this region. And we say the function f of x is totally differentiable. If and only if, so if this is the case, there exist some real numbers, m1, m2, and so on, up to mn. These are real numbers, such that we have the following asymptotic expression. F of x is equal to f of a plus m1 x1 a1. So this is x1 is the first component of this variable x, and plus m2 x2 minus a2, and so on. And m n xn minus a n plus little o and the distance between x and a as x approaches a. And we say the function f is totally differentiable on the region, open region U, if it is totally differentiable at every point in U. And if f is totally differentiable, then these constants, m1, m2, and so on, they are actually the partial differential coefficients at point A. So that is m1 is equal to partial differential coefficient at point A. And m2 is also a partial differential coefficient with respect to x2 at A, and so on. And the following theorem is also an analogous to the corresponding theorem for bivariate functions theorem. So that is, if f of x is totally differentiable at point A, then f of x is continuous at A. And we skip the proof because it's basically the same as the bivariate case. And next we define class differentiability class C1. So just like bivariate functions, we say f of x is once continuously differentiable. Continuously differentiable, once continuously differentiable, or of class C1. Of class C1. So what this means is that all the derivatives exist and they are continuous. So that is f x1, df, dx2, and so on, and dx, dxn exist and are continuous. And we can also define higher order derivatives, such as second derivative x1 with respect to x1 and x2 and so on. So in general, we have d2f, dxi, dxj. So I and j can be any of 1, 2, 3 up to n. By the way, we also write these partial derivatives as follows. Df dxi of x as fxi of x. And for this second derivative, so this means we first differentiate with respect to xj, and then we differentiate that derivative with respect to xi. And this partial derivative can be written as xj xi of x. So note the difference in the order. So xj first, xi next. Here is it's reversed. And for second derivatives, we can swap the order of differentiation if these second derivatives do exist and they are continuous. So if xi xj is equal to f xj xi, so the order is reversed. If these exist and are continuous. So this is a result that is analogous to the case of bivariate functions. And we also define R times continuously differentiable functions. Or of class CR. So what this means is that if there's a function f of x and this is differentiable up to rth order, and if those derivatives are continuous, then we say this function is of class CR or R times continuously differentiable. And if the function f is differentiable and up to any order, and all of them are continuous, then we say it is of class C infinity, just like bivariate functions. And of course, this is also called smooth functions or infinitely differentiable functions. Now let's consider more general functions from n-dimensional space to the m-dimensional space. And in particular, we consider class CR functions. Okay, as you can expect, this means R times continuously differentiable. What does it mean actually? So for these maps, we can write something like this. So x is equal to f1 of x, f2 of x, and so on, and fm of x, where x is, of course, an n-dimensional point. Let's write like this, x1, x2, and so on, n-dimensional point. Okay, so we have m functions defined on some open region in the n-dimensional Euclidean space. Now, if all of these functions, f1, lowercase f1, f2, up to fm, if they are f1, f2, and up to fm, if they are CR functions, that is R times continuously differentiable functions, as we have just defined above, then we say this map from Rn to Rm is is a map of class CR. Next, we consider composite maps of general maps. That is, suppose we have a n-dimensional space and m-dimensional space and l-dimensional space. And in this n-dimensional space, we have a subset that is an open region U. And here we have an open region V. And some map is defined here. So map F and map G. Okay, so we want to compose these two maps, F and G. So suppose f of x can be written as f1 of x, f2 of x, and so on. And since this is m-dimensional, we have m functions here. And where, of course, x is an n-dimensional point. In the open region U. And g of y is written as g1 of y, and g2 of y, and so on. And since this codomain is L-dimensional, there should be L functions. And y is a point in the m-dimensional space. In the open region V. And as you can see in this figure, we assume that the image of U by F is a subset of V. Okay, if that's the case, we can compose F and G as follows. Okay, so we compose G after F. That is a function from U to the L-dimensional space, and we define this map as follows. G after F. So a point in U, so that is X, is defined as this, H1 X, H2 X, and HL X, where H1, H2, HL, each of them is a composite function. Okay, defined by this. So hk, so k is 1 of 1 to up to L. Hk of x is equal to gk of f1, x1, f2, x, not x1, x, and fm, x. Okay, so it's just simply, if we pick a point in U, then this is mapped to some point within V, and that point is mapped to some point in RL. So that's what we are writing here. So this is X, and say this is Y, and this Y is mapped to, let's say, Z. Okay, so hk is, let's say, zk is hk of x. Okay, and z is z1, z2, and zl. So each of these is defined in terms of this composite function. Okay, next, let's consider differentiating these maps. First, let's consider the map F. So if we pick one point in U, x1, x2, and so on, xn, this is mapped to this point. f1, f2, and so on, fm. So for each of these dependent variables, we have n variables by which to differentiate. So we have the following partial derivatives: f j dxi of x, okay, where I is 1 to up to n and j is 1 to up to m. So we have n times m derivatives, partial derivatives. And this can be neatly summarized as a matrix. It is actually more convenient. So formally, let's write this matrix as this, df dx. Of course, this f is a vector function, and this x is a vector. So a derivative of a vector function with respect to a vector. So formally, this can be written as a matrix, like this. So df1 dx1 and df, what is it? df1 dx2 and df and so on, and df1 dxn and df2 dx1 and df2 dx2 and so on, d2 dxn. So we do this on, and in the last row we have fm xn, fn, wait a minute, x1 here, x2, and fm, sorry, and xn. So this is the matrix, and this form of this kind of matrix is called a Jacobian matrix. And we can do this for the map G. So for map G, we have a point in the open region V, y1, y2, ym. This is mapped to g1 of y, g2 of y, and gl of y. So again, let's write the partial derivatives in the form of the Jacobian. So that would be following. So dg1 dy1 and dg1 dy2 and so on, and 1 ym. So d2 g2 y1 g2 dy2 and so on. dgl dy1 dgl dy2 dgl dym. So this is a L by M matrix. So there are and L times M partial derivatives for this map. And we do this for the map, the composite map. So we have a point in the open region U, Xn. So this is map to H1, H2, and HL. Okay, so G after F. And again, we can write the Jacobian of this composite map. Okay, so that is H1, X1, and H1, X2, and so on, H1, Xn. So this is the Jacobian. Now our goal here is to express this derivatives of the composite function in terms of the derivatives of each component, f and g. So in other words, we want to find the chain rule for the composite maps. Actually, this chain rule can be expressed very neatly in terms of matrix multiplication. That is, so this matrix is actually expressed as follows. G, Y, and F, and X. So this matrix, okay, this matrix is this matrix, and this matrix is this matrix, and this matrix is this matrix. So they're Jacobians. So the Jacobian of the composite function is a product of Jacobians of the components. That's very clean result, in my opinion. To write more concretely, so let's pick any elements of this Jacobian matrix. So that is DHK dxi. So this is an element of this Jacobian matrix. So this, by the definition of the matrix product, this can be expressed as follows: from J1, J equal to 1 to J equal to M. And this matrix element is dgk and dy j evaluated at this position. Okay, and dfj and dxi evaluated at x, evaluated at x. So this is the chain rule of the composite map. And the proof of this is rather straightforward. You can just intuitively extend the proof of the bivariate function. So I will just skip it. And if you have studied linear algebra, you know that the product of matrices is actually a composition of two linear maps, right? So, and also we know that the essence of differentiation is linear approximation of a function, okay? So what this equation means, this chain rule indicates, is that the derivative of the Jacobian or linear approximation of the composite function is a composition of linear approximations. Okay, so this is a linear approximation of the map F, and this is a linear approximation of the map G. And their product is the composition of these two approximations, two linear approximations, right? So the linear approximation of composite function is a composite of linear approximations. So that's very easy to understand, intuitively easy to understand. All right, that's all for this video. See you later.